Now let's do a justification, don't think we can call it a derivation, for the Nernst equation. If you'll remember from the thermodynamics chapter, we had an equation that said that the delta G reaction equals delta G not reaction plus RT ln Q. And we said that the delta G not reaction was at standard conditions, though it could also be used at different temperatures. But everything, including concentrations and partial pressures, was standard. And we use this Q term, where Q is the reaction quotient, to adjust for concentrations and partial pressures that were not standard, not 1 molarity or 1 atmosphere. Now, if we go ahead and take this equation and divide both sides by before we do that, we have to say that we have an equation for delta G, and delta G not equals minus NFE not cell. So we can make a substitution here. We can do the same thing without knots here to get an E cell that is not standard and allows us to adjust for non-standard concentrations and partial pressures. Well, we're not quite done. Now we have to divide through by minus NF. To get what's called the Nernst equation, and it says that E sub cell equals E naught cell, the standard cell potential, minus RT over NF ln Q. And this is what's called the Nernst equation. And it allows us to adjust for different concentrations. And again, what we'll find, and this is no coincidence, that even if we are not at 25 degrees Celsius, we will still use E naught cells. And here the justification is that even if you're away from 25 degrees Celsius, the cell potentials are pretty close to what they are at 25 degrees Celsius. And there are times, by the way, that we will be far away. And these will be estimates. If we wanted better estimates, we'd have to take a more advanced chemistry class to learn how to adjust those. Much more advanced than we're doing here. So that's the Nernst equation. Now let's start using it. And we're going to use it to determine the cell potential in volts for this reaction with concentrations that are clearly not 1 molarity. And this will be a two-step process. First, we need the cell potential of the reaction under standard conditions. Then we will fill in with our different concentrations. So let's see, we have 3 plus. All right, so our oxidation and our reduction half reactions. Our oxidation is going to be, we're taking iron solid and turning it into iron 2 plus, which must have a change of 2 electrons. We're also taking iron 3 plus and turning it into iron 2 iron 2 plus. That's going to be a 1 electron process because the charge is changing by 1. And now let's see if these are on the table for our let's see. So we do have iron 3 plus going to iron 2 plus. That has a cell potential of 0.77 volts. And I know that was probably hard to see. So let's go ahead and zoom in. Here's iron 3 plus going to iron 2 plus, 0.77 volts. We're also going to use as our oxidation this iron reaction shown as a reduction at minus 0.45 volts. Of course, we're going to turn that around and change the sign. And our cell potential doesn't change. I'm going to go ahead and add up my overall reaction. I need to do that because my Q will have coefficients in it. So times 2. And I have well, let's do it in the order they have here. So 2 iron 3 ions plus iron solid. My electrons cancel out, and I'm left with 1, 2, 3 iron 2 ions. With a standard cell potential, and I'm not sure I trust myself to add this up unless I use a calculator, 1.22 volts. So now let's figure out the cell potential at non-standard conditions using the Nernst equation. We know our standard cell potential (1.22 volts). We know RT, so R is 8.314. And remember, R is only ever the other value, the 0.08206, if we're talking about using the ideal gas law. Our temperature, while not given, may be assumed to be 298. Room temperature, or standard temperature, close to room temperature. Let's see, N is 2 because we canceled out 2 electrons, and F, 96,485 Coulomb per mole electrons. Let's see, so my kelvins cancel out, my moles cancel out, and I have joules over coulombs, which will be volts. Now let's plug in my ln here. I'm just going to write out my Q down here, and then so I can plug it in up here. So Q is going to be concentration of iron 2 ions cubed over concentration of iron 3 ions squared, ignoring my solid. And again, Q is for any concentrations that were given in a problem. So my Q is now going to be Fe2 plus 1.2 cubed over 0.010 squared. Our units will cancel out. I'm still going to write them in. Or let's say this. We've talked about units for Q and how they work. Let's find this big term first and then subtract it off of our 1.22 volts. I've got 1.2 cubed times 1.2 squared. Then I've got 0 divided by 0.01 squared, 17,280. Take the natural log, times it by all these numbers, 8.314, 298, divided by 2 and our Faraday constant, and I get 0.125 or 0.13 when I actually do 2 decimal places here. This is going to be 1.22 volts minus 0.13 volts. Is that right? Goodness. Good. 1.09 volts is our final answer for the cell potential under non-standard conditions given in this problem statement. And what we can see is if you want to have the potential, the biggest thing that affects the potential is your half reactions. And that's true of the free energy when we were talking about thermodynamics. The biggest thing that affects your free energy is the reaction itself, and you can fine-tune that potential using the conditions that you use. So these conditions have a lot of products and not much reactants, so it's going to decrease the potential. Still positive, still spontaneous. We'll talk about pH meters next.